Okay, let's briefly talk about real gases. We talked about the kinetic molecular theory, in which we said that gases have negligible volume. But what we find is real gases, they have volume. And when we talked about real gases versus ideal gases had no interactions between them. But we find that real gases do have attractions between gas particles. Molecules or atoms, right? So, where do we see this deviation from the ideal gas law? Well, if gases have volume, let's take a look at the ideal gas. And a real gas. This is my real gas. Then, turns out that as I continue to increase my pressure, at some point you find that the volume doesn't go to zero. There is a definite volume. Whereas for something ideal, as I increase the pressure, at the limit, this should approach zero. So what we find is that the volume of my real gas is greater than the volume of my ideal. Okay? And normally when we're in this situation, you can't really tell. Because remember, before I said it was definitely less than 1% of the volume. But when it starts getting a higher percentage of the volume, that's when we start seeing the effects of real gas. Okay? So we know that the volume for real is greater than the volume for ideal. Okay? It's an A and an L. Let me just make sure it's legible. Ideal. Okay. Now, let's take a look about this attraction. How does the attraction between gas particles affect my gases? So, if we look at my ideal situation, let's suppose I have 10 particles . So the pressure, this is my pressure for the ideal. If we look at something like my real, what can happen is this. Because there's an attraction for a short period of time, some of these particles will hit each other. So these would act as one when it hits the wall. This one's okay, this one's okay, that one's okay. Look it. That will act as one. This acts as one. So when we look at, because of the attractions, when we look at my real gas, and we look at the pressure of the real gas, instead of having 10 particles hitting my walls, I'm going to have 1, 2, 3, 4, 5, 6, 7 particles in this situation that I've drawn. What that means is this, that my pressure of my real gas is less than the pressure of my ideal gas. Okay? So how do we put that all together? So the pressure of my real gas is less than the pressure of my ideal gas. Okay, this is how we put it together. Suppose we take my ideal gas law. So, here's my ideal gas law right here. PV is equal to nRT. If we're looking at real gases, then what we need to do is come up with an expression that incorporates the real gases to substitute into my ideal gas. So what happens is this. For my ideal volume, because my real gas is larger, what we're going to do is we're going to add some term, like the number of moles of gas times some factor B. And that's going to be equal to NB. Okay? So, my ideal gas expression for the volume will be V minus NB. Okay? What about pressure? Well, if the pressure of my ideal gas is larger than my real gas, then I have some term like AN squared over V squared. And that's equal to the pressure of my real gas. So the pressure of my ideal gas is equal to P plus N squared A over V. Okay? And what this is, V squared, right? Wrote it down. Okay, so what this is we're substituting for the ideal the expressions where we're using our real values. Okay? So when we do that, we get this equation. P plus N squared A over V squared times V minus NB is equal to nRT. And this is called the van der Waals equation for real gases. Okay, now, this is all great, so what do we do with it? Okay, so we'll do a calculation with it, but just let me just tell you, what about these values? So, N, P is the pressure of our gas, N is basically the number of moles of gas, V is the volume of the gas, A is a constant, and that, though, is dependent upon your gas. So A, you need to look up. V again is volume, N is the moles of gas. B is also specific towards the gas. Okay, so those are going to be given to you. In fact, this formula you can look up.